All right, last time we were not here. We were talking about the course class. We wrote this method here, find. But remember, find was special because it started with an underscore. And that meant that, it's a method that exists in this class, but it's only meant to be used within the class. It's not intended to be used outside the class. And it's the same thing with attributes that begin with an underscore as well. They're fine to use within the class, but they're not intended to be used outside the class. They're important for the inner functionality of what's going on, but you're not supposed to access them directly. That's what the underscore means. And we wrote find because it just does a linear search, and it tells me the index where something exists, or -1. And here it's returning -1. In the example I did, we switched it to some constant not found, right? Because why not make your code a little more clear? And the reason we made it a separate method is because we're going to need that. We're going to need a linear search for two other methods we do want to include, contains and remove. Contains just tells me if a given a given student exists within the collection. So all I have to do is just call find. That's all it is. And check if it returns -1 or not. If it returns -1, we didn't find it, meaning it's not there. And then this method would return false. If it returns anything but -1, that not found, it'll return true. So we're good. And then remove. Remove has kind of two parts to it. The first part is, well, if they tell me to remove something, first I need to make sure it actually exists. And if it does, we say self.students. That's the list that contains the students. And then we use pop. Pop is a method that just removes something at a given index from a list. And which index do we want to remove? Well, the index where the student we want to remove is, which we can get by calling find. And just note here, this is a good use of raising an exception. What do I do if someone tries to remove something from this list, but it doesn't exist? Should I crash? Should I ignore it? I don't know. It's not up for me to decide. It's up for the person using my class to decide. So all I can do is say something funny happened and let them deal with it. Otherwise, if it does exist, we're good. We just remove it. Any questions on that one? This is where we left off on the remove. So that was just recap. Okay, now the repr. All right. So this right here is a common pattern you'll see for reprs for collections like this. A collection is just a fancy word to mean a data structure that contains some collection of information. It's a collection. This is a common pattern. I mean, if we think of the list, think of what the list's repr must be. When I print out a list, the first thing you see is an open bracket, right? The square brackets. So an open bracket followed by the string representation of whatever the hell's in the list, one after the other. So the repr for the list actually has to keep getting the string representation of each thing in the list. And that's what we're going for here. Ignore line 31 for a moment. For each student in the collection of students, in the list of students, I get the string representation of that student. Here, actually, let's change this a little bit. I'm going to change this to be I haven't run any of this yet. Okay. I'm going to change this a little bit right here. Yeah, I see you're mad. Course name, there we go, /n. And maybe for the fun of it, I'll do this. So it'll start as the name of the course. Then we go to a new line. And then for each student, we are saying S plus equals, which of course just means S equals S plus. This is just basically keep appending to the back of that string. Append to that string a string representation of the student at the beginning of the list. New line, the next student. New line, the next student. New line, the next student. So the repr for this course is also making use of the repr for the student class, because that's right here, because it's an F string, it's getting the string representation of the student. So this actually calls the repr for the student class. We're calling it for each individual student. And then once the loop is done, we return S. And remember, repr doesn't print anything. It returns the string. Remember that. A lot of people mix that up. But I run this, it should be happy. Yep. Take a moment and look at that code and make it make sense to you. And this is the output. And you should be able to see the relationship. You should see the one-to-one, you should see how this maps to that. The name of the course, new line, append to that string, tab, the string representation of the first student. Well, the first student was Bob Smith. So we see Smith, Bob, tab, their student number. New line, tab, student. The next student is Jane Doe, Doe, Jane. We get this funny here because of just the nature of tabs, right? That's just, it is what it is. And yeah, that's that. I mean, if I can get rid of that inside this tab, maybe we don't need that. And maybe I should have a colon here or something. There, now it looks a little bit different. But this is a typical pattern that you see for a collections repr. If it's a collection of several things, okay, well, the string representation of the collection of several things also needs the string representation of each of the things. Questions? All right. Notice that we're not writing an equals for this, the underscore underscore EQ. Turns out, in general, defining a quality for things can be rather tricky. And this is especially the case for collections, because there's a lot you really have to think about. Like, you might think, well, just check if the course name is equal and check if the lists are equal. And you're right, that could work, but should the order of the students in the list matter for if the courses are equal? Maybe. Maybe it should. I don't think it should. In terms of what I'm imagining a course to be, the course is just some collection of students. It doesn't really matter. So I really don't think it makes a lot of sense to I don't think it makes a lot of sense to care about the order, so just checking equality on lists could be tricky, and so it's actually quite complex to do equality for something like this, so we're just going to skip it for now. But be aware that we totally could write it, it's just a little much for right now. Any last questions before we move on? Any last questions about objects, classes before we move on? Because we're about to move away from them now. All right. All right. So I will say, and be very careful in interpreting what I'm saying. Objects, like classes and objects, they are the last big topic that this course covers. The next two topics, because there's only two left, I think, maybe three. No, the next two topics they're not new, but we're revisiting things. I mean, when we get to the searching, or sorry, the sorting, it's new. Don't get me wrong, that definitely is new. But they're more taking a step back to where we were before. Because before, we just spent time talking about data structures, objects and data structures, which is a collection of data, and that includes things like lists, sets, tuples, dictionaries, and they're very important. And obviously, if you crack open those data structures, you look under the hood, you'll see a lot of algorithms underneath. But I know I've said this before, but we're interacting with those data structures algorithms at a more abstract level where we really think of them as just the data structure. We really think of the list as the list. We don't think of the list as the underlying algorithms, right? And so we're often using algorithms with these data structures. They go together. For example, if you're doing a linear search, maybe you're doing it on a list, right? Well, the linear search is going to have to iterate over some data structure. So these things go together. I realize, obviously, underlying in the data structures, there's algorithms, but it's all about at what level of abstraction we're reasoning about these things. And let's take a moment and reflect on everything we've learned so far. Raise your hand if you had any programming experience before 161. Really high, I want to see. 1, 2, 3, 4, 5 people. Okay. So less than, like, what, a third of the people in the course are in this lecture hall right now. Of you, put your hands up again. I want to leave them up for a sec. So yeah, 1, 2, 3, 4, 5. So of those with your hands up, leave your hand up if you are comfortable enough to say, well, I had programming experience before, and it was like, it wasn't like, oh, I programmed a little. Like, no, you've done it enough to say, how do I word this? Like, you didn't just tinker a little bit. Like, no, you did it in like a course maybe in high school or something. Okay, so that leaves 4 people. Okay. So for the most of you, you haven't programmed before. And let's take a moment. You can put your hands down now. Sorry. For the most of you, you started by writing hello world. And that was like your first program. And since then, you've gotten familiar with some programming environment. We were using Colab. We learned about values. We learned about types, variables, right? You know about print and input. They're also both functions. We know how to get data out of your program. We know how to put data into your program with input, even though we don't use it very often. You've been making use of functions, not only the functions that already exist, but you've written your own functions and you've made use of them. You've learned the basics of like logic and how to use, oh, there's a typo there. Use if and else. So we learned about like basic logic in terms of like the Booleans, ands and ors. We learned about if and else. We learned about loops, for and while loops. You learned how to use objects. And we also learned how to make our own objects. We learned data structures, things like lists. You're pretty familiar with those by now. You know how to read and write data from a file. You've learned how to write classes on your own. I just said that. And chances are, so like obviously you can write your own programs now. You can write your own code. And chances are, if you stumble upon some Python code someone wrote, or if you just go through Python's existing code base, you go through Python's standard library and you look at some of the code in there, if it's well written, because there's a lot of poorly written code that no one's going to understand, but assuming it's well written, you probably, at this stage, you could probably figure out what it's doing. Maybe not 100%, but you could probably figure out what it's doing. And of course, you've learned about testing. You know how important it is to test your code. You know how to debug your code. There's a lot that you've done. Point of all this is you've done a lot. And to think less than 3 months ago, you wrote Hello World. So whether you like it or not, you've learned a lot. Keep up the good work. And the reality is, when it comes to, if you think of a programmer's toolbox, obviously an experienced programmer has a really full toolbox. They know how to use a lot of these things. But the overwhelming majority of tools that they're using on a daily basis, you know. You already know it all. They don't have a lot more sophisticated tools than you do. They've got a few more, don't get me wrong, and you'll learn them if you keep taking more programming courses. But the reality is, you are all pretty competent programmers, assuming everything's going well and you're following along. So you know a lot. You really, I don't know if you know this, programming it's kind of hard, right? Who here thinks this is easy? Usually there's one asshole. All right, it's you. It's not, right? There's a reason why programmers are paid big bucks, right? Because if everyone can do it, everyone would do it. But not a lot of people can do it. It's tough. Now, that doesn't mean it's overwhelmingly difficult. No, that's not the point I'm making. The point I'm making is it's not trivial. It takes skill, it takes time, and you've developed these skills, and you're going to continue to develop these skills over time. So yeah, the last few topics have been very heavy on data structures. And yeah, I just said that. The focus on algorithm tools. Okay, here we're going to start to shift the focus back to algorithms a little bit for the last little bit of the course. And how we can use all the tools we've learned to solve more interesting problems. Further, we will take time to think about this is a good one too. We're going to take a moment to really try to show what it means for an algorithm to be good. So let's go back to linear search. We've talked about this to death. We're going to keep talking about it. So given the familiarity of the problem in linear search algorithm, we'll start to... Linear search is usually the first, big isn't the right word, but the first core general purpose algorithm programmers learn. And then the ones that come after that are usually some sorting algorithms. And you might think linear search, well, it's trivial. Well, I wouldn't say it's trivial. I would say the problem itself, and here's another thing too, make sure you're separating problem from algorithm, right? The problem of searching through a collection to find something is easy to understand. The problem, you're all familiar with it. And the reason we like this algorithm is because you're already all familiar with the problem. But look at what this algorithm here needs. First of all, it's defined in a function. It's making use of a for loop. It's making use of an equality check. It's making use of conditions. And we've got a data structure in there. There's a lot that you need to know for this to make sense as well. But when looking at this code, we got haystack, we got needle. For each element in the haystack, if the element I'm currently looking at is the thing I'm looking for, needle, return true. If I ever finish that loop and I didn't return true, that means, well, I never found the thing I was looking for, which means the thing isn't there. That's your general purpose linear search. Obviously, we've also seen some variations of this linear search, like we just saw find, which returns the index of the thing, not just a true false, but the index. We've seen ones in lab where you're doing a linear search to check if everything in in the diagonal is one thing or the other, right? That's a variation of a linear search. So they're all, a lot of the algorithms that we've seen so far, look, assignment 1 was a variation of linear search. Assignment 2 was a variation of linear search. Assignment 3 was a variation of linear search. And who here started assignment 4? There's a bunch of linear searches in there as well. Variations of linear search. It's not as explicit as this, but linear search is kind of a big deal. Obviously, when you started assignment 1, you weren't really thinking of it as a linear search, right? I kind of gave it to you. Okay, here's a loop. It looks at each thing. You just got to do the check. But you're not checking if it's equal. You're checking if it's within some box. But it's the same idea. For each thing in a collection of things, check something about it. So we'll just do this together here. Having a correct algorithm for a problem is clearly important, but we also want to make sure we have a good algorithm. We also want to make sure it's well written as well. But what does it mean for an algorithm to be good? And a lot of times when we talk about this, we're talking about it in the context of resources. How much resources does this algorithm take to execute, to solve the problem? You heard that, right? Okay. It's not like an alarm or anything, is it? All right. If two people have two algorithms to solve the same problem, but their algorithms are different, and one takes less resources than the other, that's probably good. But programmers are, we're not going to get into this too much, but programmers are pretty lazy. When it comes to analyzing how much resources something takes, we're pretty generous in what we consider equivalent amount of resources, but we'll learn about that next semester if you're in 162. Raise your hand if you're planning on taking 162. Really high, I want to see. So we got 1, 2, 3, 4, 5, 6. So everyone else, what's wrong? What? Yeah. Oh, is that the trick? That's why no one else wants to? Yes, it is a prerequisite. So, and by the way, if you thought 161 was fun, here, let me take a pause. 161, don't get me wrong, I like the course. I think it's fun, I think it's great. People get to learn a really interesting, new, very important skill. But I think 161 compared to 162, I think 161 is painfully boring. I find 161 so dull relative to 162. 162 is so much more interesting. And the reason it's more interesting is by that stage, everyone kind of knows how to program. And because of it, like to me, part of the fun of like these types of courses is like the problem solving. Sometimes these questions are almost like little riddles you kind of have to like tease apart and solve, right? And it's always kind of fun to solve those things. I always liked it. Because we know more, next semester, the problems that we could start to solve are more interesting. So they're more fun to solve. And we'll learn some interesting algorithms that are, I think they're kind of neat. For those of you also that are a little worried of 162 because of a change in the programming language, don't be. You really don't need to be. At the start of the semester, everyone freaks out. Just 1 second. Everyone freaks out because it's a different language, and then like a week in, maybe people are like, "Oh wait, yeah, no, you were right. It's nothing." The switch. The algorithms, the code's basically the same. Yeah.
You use Java for 162.
Yes.
Okay. What do you run it on?
Pardon?
What do you run the code on?
What do I run it like with?
Yeah.
So we're going to run it locally. When I say locally, I mean like on your computers. And to do that, usually what you do is you install the JDK, the Java Development Kit. So there's the JRE, the Java Runtime Environment, and if you have any programs written in Java on your computer, in order for those to run, you need to have a JRE installed. Most operating systems come with that by default. If not, maybe you've downloaded it Back in my day, you used to have to download it separately. It was a whole thing. But being able to run it is different than being able to write code, compile it, and then run it, right? So you need something called a JDK, which you can just go download. But we're using, I don't know, probably the most popular, don't quote me, but probably the most popular programming environment for Java called IntelliJ. It's really good. It's like what people use in industry too. With that, there comes like a billion bells and whistles that you're never going to want to look at. So it can feel a little intimidating at first, but once you kind of learn the things you need to know, it's a joke. But the IDE will actually install Java for you, so you don't even need to think about it. It's good stuff. Anyways, I lost my, oh yeah. So just for context, assignment 1 in 162 is effectively the exact same assignment. There's some tiny little differences, but effectively the same assignment as assignment 4 in this semester. So you get a chance to do the same thing, just in a different programming language. So you get to see, you get a little bit of time to explore that. Also, the first few topics are like, here's Python, here's the same thing in Java. Here's Python, here's the same thing in Java. So we do that a little bit to kind of help you switch. The second assignment is a maze solver. You use some very basic artificial intelligence to solve a maze. And then the third assignment is another maze solver, but you use a much more interesting form of artificial intelligence to solve a maze. You use something called A-star. It's like a pathfinding algorithm. It's AI. And the last assignment, I can't even remember what it is anymore. Oh, it's Huffman codes. That's fun. Anyways, we'll see that later. There was one other thing I was going to say about 162, but of course I forget. Whatever. Does anyone have any questions about that while we're on the topic of next semester? All right. Well, if you think of any. All right, back to linear search here. So if I have how much, okay, when we talk in terms of the amount of resources our algorithms need to solve a given problem. And less resources is better, because less resources usually means like less power, and using less power is good. We don't want to use as much electricity if we don't have to, like, but also because it also takes less time. Yeah?
We don't need to use a function to do a linear search.
No, you could, assuming you have these that exist just as variables, this could be outside of a function. You're right. It doesn't need to be in a function. Yeah.
No, but do you need to use just a function in general?
No, you don't need to. You could. It's just to...
I'm just thinking of another way to do it, but I wouldn't use a def statement or anything.
That's probably fine. You could probably do it without a function. Easy. Sorry, you absolutely could do this without a function. Yeah. I just like it because it's a great way to give a name to that chunk of code. Someone looks at this and goes like, oh, it's a function called linear search. Probably does linear search. Yeah. Usually when we're talking about the amount of resources an algorithm uses, is like in terms of runtime, no one's sitting there with a stopwatch. No one's measuring the amount of milliseconds. Usually what they're thinking about is time complexity, which is what we've talked about a little bit before. If I have a list that's size 10, and I tell you, search for this thing in this list of size 10, how many things do you have to look at to guarantee you find it or not? Come on, wake up. 10. Of course, it's 10, right? If it's 20, how many do you have to look at? 20. If it's n, how many do you have to look at? If we double n to make it 2n, how many you got to look at? So this is what we call linear. The amount of time it takes is linear and scales linearly as the input size changes. And there's a bit of a nuance here. It's important that a lot of times people think oh, that algorithm takes n steps. And yeah, it does. If I have a list of size n and the number of things I have to look at is n, it's linear. But there's a little bit more nuance to it. A lot of times we're more concerned with how does the amount of work change relative to the input size. So as the input size grows, the amount of work grows the same rate, linearly. As this doubles, the amount of work doubles. Yeah?
Random question. If there is such a thing as linear search, is there such a thing as exponential search?
It's not an exponential search, but your brain's kind of in the right way, and we're going to see it shortly. In fact, you actually already know this algorithm, whether you like it or not. Does anyone have a textbook? Handy? Not this one. I mean like a physical textbook with them? You do? Here, do me a favor. Can you just open it for a second? Just get it and show it to me for a second. We're skipping ahead in the content just a little bit, but this is just because, what time is it? 11:02. Okay. Everyone look at that textbook. It's pretty big. Just hold it up so that everyone can see. Actually, could I just borrow it for a second? I'll come and grab it from you. That's a big one, too. This is perfect. Thank you. What do we got here? Ooh. Is this for 135 or whatever? Yeah. Out of curiosity, does anyone else in the room have a textbook with them? No. Of course, no one buys textbooks. That's weird. All right. I want to find page, how many pages are in here? Almost 1,000, right? Actually, no, over 1,000. 1,000. 1,093, 94, come on. 1,095, 96 if you count the last one too. There's a lot of pages in here. And you tell me to turn to page, if you tell me to turn to page 500, do I do this? No. No, that's not it. No, still not there. No. 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 Is this how I turn to page 500? No, this is ridiculous. This is stupid. But this is a linear search. Is this the thing? No. Is this the thing? No. Is this the thing? No. I'm doing a linear search. But what would you do? I'm going to guess you go something like this. All right, well, it's probably around halfway through. Let's see, probably about here. Let's see. Nope. I'm looking at page 339. All the pages over here are less than 339. All the pages over here are bigger than 339. And I'm looking for 500. Do I look over here? No, that's stupid, because 500 is bigger, so obviously it's not in this side. So let's go again. Okay, if that's 300, let's see. Oh, I'm on page 527, right here. Oh, I messed up, actually. Hold on. I should have kept track of where 300 was and something. Let's see, it was like this. Okay, here. So here's all the pages bigger than 527. And here's all the pages between 339 and 526. And I'm looking for 500. Where do I look? Here, right? How many pages did I just eliminate from my search over here? Like 500, right? Like quite a bit. Yeah, so let's see. If it's between there and there. Okay, so if that's 300, it's probably, I don't know, around here somewhere. Oh, 475. So all the pages here are between 339 and 474. And all the pages here are between 475 and 526. 500 is obviously here. Every time I get a little closer, 484, 496, 502, 500, found it. That's how you find that thing. That's how you found page 500 in that book. I didn't do a linear search. Think about this for a second. Let's go back to the linear search. How many pages do I eliminate from my search every time I look at a page with linear search? No, no. How many do I eliminate? One at a time. Is this it? No. That page is, I know it's not there. With that other one, when I was looking for page 500, I'm looking at 572. Let's go. I was always looking at this side. 573. I'm looking for page 500. I know page 500 is clearly on this side. So I'm going to continue looking on this side. Over here, I've got page 573. I've got like almost 500 pages right here. No, I've got like more than 500 pages right here. How many pages did I eliminate from my search with one look? Like 500. All of these don't matter for me. I know what I'm looking for is over here. So with this strategy, I was able to find the page way faster than doing a linear search. But like way faster. And if you're wondering, well, how can it be fast? Like what's faster about it? Well, it's faster because I'm able to eliminate chunks of the search each time I look at the thing. I'm able to eliminate 500 pages with one look as opposed to one at a time. So that's how it's faster. But there's a bit of a catch. There has to be something about the data I have. There has to be a property of the data that I have in order for this search to work. Anyone have a guess to what it is? Imagine instead this was a phone book. Okay? You know what a phone book is, right? Okay, good. They don't really make them anymore, right? But imagine it was a phone book, and I'm looking for Hughes in the phone book. And I turn to L, right? Well, if I've got it, if I've got L, I know H is over here, not over here, because H comes before L, right? I knew page 500 was over here because it came before 574. Right? So there's something about the data that has to be true in order for this search to work. But we'll come back to that. Let's go back to linear search. I spoiled the fun. All right, linear search. Yeah. So what's the best case scenario? If the worst case scenario, when I was talking about linear search there I said, how many things do you have to look at to guarantee you find the thing or not? All of them. That's like the worst case scenario. What's the best case scenario? How many things would you have to look at in the best case scenario to see if something exists or not? One. The first thing, and it happens to be the thing you're looking for. So there's a best case scenario, there's a worst case scenario, and on average, let's say, assuming the thing does exist in the collection, on average, that thing is going to be like in the middle, right? Not literally in the middle, but for every time it's the first, it's the last. For every time it's the third last, right? On average, it'll be in the middle. How much? So this algorithm has a time complexity of n. We say it's big O n. It's on the order of n. That's just the terminology computer scientists use. And another thing that computer scientists like to think about when they think of resources is space complexity. How much space does this take up? And this one, you might think like, well, how the heck am I going to think of that? It's actually fairly straightforward a lot of the time. If I have a list of size n, what do you think the space complexity is? N. I need n units of space to store that list. So that's space complexity. But often we like to focus, at this stage, we really like to focus on time complexity most of the time. And often there's a bit of a trade-off. A lot of times, You might have an algorithm that has lower time complexity but requires more space. Well, you might have an algorithm that requires way less space but takes a little bit more time. A lot of time there's no silver bullet. Sometimes there is, depending on the problem. But a lot of times we're making these judgment calls. We're making these design decisions. There's always a trade-off. Sometimes in funny cases, especially with like parallelism, we'll think of like processor complexity. How many processors does your algorithm take? Like if you're like, well, my algorithm actually doesn't take n units of time. It takes 1 unit of time, but it requires n processors. And you're like, well, I don't have a billion processors, so. But usually we're focusing a lot at this stage on time complexity. All right, yeah, the above highlights a major idea discussed the goodness of an algorithm. More precisely, we call it computational complexity. So then there's time complexity, space complexity. It's all about the resources. To keep things simple, it's common to think about the worst case scenario too in the analysis. We're really always focused on the worst case scenario. Okay, we also like the amount of work. Okay, so here's the linear search. If a haystack is length 10, loop needs to run 10 times, worst case scenario. If it's length 100, it's got to run 100 times. 10 million, 10 million. If it's n, it's got to run n times. For the space complexity, it's just n, assuming a haystack has length n. Yeah. Now, this is going back to what we were talking about a moment ago. It's very related to what I was doing with the book. And don't worry, I remember I've got your book. We'll get it back to you. I'm going to use a calculator because I'm lazy. I need a volunteer. Okay, you're going to pick a number between, for simplicity, you're going to pick a number between 1, I know this says 0 in 1023, but to keep it simple, pick a number between 1 and 1024, okay? Don't say it yet, keep it in your head, all right? Tell it to the people behind you so they know, but I'll plug my ears. I won't listen. All right? If I was doing a linear search, this is how I would search for it. Okay, is it 1? Is it 2? Is it 3? 4? 5? 6? 7? This isn't very good, right? This is clearly not very effective. Worst case scenario, how many things am I going to have to guess? Well, 1024 because we started at 1 and I changed a little bit, but yes, right? A lot. But I can get it in 10 guesses. I promise you. I can get it in 10 guesses, but there's a catch. You have to give me one thing, all right? Every time I make a guess, you got to tell me, is it higher or is it lower? All right? That's the trick. Okay? So, here's my first guess. Is it 512? Okay, well, you broke it. Okay, pick another number, you jerk. You ruined the fun. All right, pick another number. You got another number? Tell the people behind you. So, for those of you, when I said 512, if you thought it was a magic trick, that was just dumb luck. Well, he knew what I was going to do, so he kind of spoiled the fun and blew your mind, apparently. So what I did is I guessed the number right in the middle of 1 and 10,024, which is 512. So there was a reason I picked that number. It wasn't just like I'm a genius. I just knew. No, I love how for a moment you were like, okay. I'm going to start with the same thing. Is it 512? It's lower. Okay, is the number 256? Higher. Is it 384? Higher. Now that was a third guess. I need someone to keep track of guesses. You're keeping track, perfect. So you said higher than 384? 448? Did you pick like, don't answer it, but never mind, I'll say it after. 480? Okay. 496? It's higher, yeah. 504? 508? 510? 511. Okay, that was the 10th guess, right? Yeah. So it's about halfway through, I was like, he picked 511, didn't he? What were you going to say?
I don't think that was 10 guesses. I think that was 9.
It should have been, hold on, let me go count. 1, 2, 3, 4, 5, 6, 7, 8, 9. Well, 510, so it kind of was 9 because when I guessed 510, there was only 2 options left. So when I guessed 510 and he said no, I didn't really need to make another guess to know it was 511, but let's pretend I guessed that one as well. Yeah. So, yeah. But of course, you see what I did is I always picked halfway between the remaining elements. I picked 512. He said lower. So I knew it had to be between 0 or 1 and 512. But when he said lower, I immediately eliminated all numbers between 513 to 1024. I eliminated half of the numbers. And that's the best case scenario. You can never eliminate more than half unless you just get lucky with a guess. You always want to guess right in the middle because no matter what, you eliminate half. So when he said lower, I made a guess that was exactly halfway between 1 and 10,000, or 1 and 512, which was 256. He said higher, so I picked the number between, which was whatever 256 plus 128 is, 300 and something other, right? So I was always guessing in between. Okay, we won't have time to go any further, but I'm going to do one last trick. I need another volunteer. It's going to be you. Okay, you're going to be my volunteer, whether you like it or not. And this is what I'm going to do. This should blow everyone's mind. I'm going to give you a list. Okay, it's behind my back. And I'm going to guarantee that you're going to be able to tell me if the thing I'm looking for is in that list, okay? But I'm not going to ever tell you what that thing is. But you'll know if the thing I'm looking for is in that list. Does that sound far-fetched? Let me make clear it is. I'm about to give him a list. And he's going to tell me if that thing I'm looking for is in the list, but I'm never going to tell him what to look for. And he's still going to know. How? Okay, are you ready? Okay, here's your list. It's an empty list. Is the thing I'm looking for in that list? See, he knew. Yeah. And if you're like, okay, well, that was dumb. No, it wasn't. That was genius. And you'll see why tomorrow or whatever the next lecture is. Anyways, I'll see you all later.